So this is what we talked about yesterday, right? We started from explaining this lab question, and also we started in chapter 1, motion in 1 dimension. And remember, the reason we start from there is we focus on mechanics, which is the most fundamental branch in physics. And in mechanics, we study motion. So we will start from talking about describing a motion, so which is called kinematics. And then after that, we'll go to explaining motion, so which is dynamics. So in order to describe a motion, we introduce a couple of quantities: time, displacement, velocity, and acceleration. So they can be summarized like in this here. So most of the quantity we use in physics, in mechanics, are vectors. Okay, displacement, velocity, acceleration, they're all vectors. Okay, time is a scalar on the other hand. Okay, now the relation between the quantities that we introduce can be put in this kind of a simple relation, like to basically we have the displacement, right? And then we want to describe how the position changes, so we got velocity, and then we want to describe how the velocity changes, we got acceleration. So like they're related like that. Okay, and we start to talk about a little bit of the space-time diagram, and from that you can actually see how the motion goes, going to the positive direction or negative direction, and also you can also calculate the velocity of the motion, which is the slope. For a complicated motion like this, the slope of the tangent line still tell you the velocity, but that velocity is changing all the time. It's not a constant. Okay. So let's continue to discuss this chapter 2 stuff. So as I said, we were almost done, but let's talk about this space-time diagram. Okay. We've done this, right? So this is all these things. Now in the homework, you're gonna be given some a few problems related to these kind of diagrams. On these, you're given a coordinate system with t and x, and with all the scales on it, and then you're gonna given a diagram of motion, something like this. I don't remember, but something. Anyway, so from there, it asks you, for example, to calculate for a specific time interval, what is the average velocity of this interval? So in that case, you just take, you just measure, you read out from the diagram what is the displacement, using the basic definition delta x over delta t. Okay, to calculate this. Okay, now there's another kind of diagram, which is a diagram of velocity versus time. Okay, this diagram is not as important as the first kind, but I think there's one problem, homework problem, like about that as well. So as you can tell, is again in this diagram, what you're going to see here is actually you have something. This tells you the velocity at a given moment, right? So as the velocity changes, as time changes, the velocity may change. Okay, so this gives you different information, but the slope of this line here actually. Okay, let me start. Let me do a simple one, like a straight line. If you have a straight line here, right? If you pick up 2 points on the line, calculate the slope, right? The slope gives let's say this is a V2 minus V1 divided by T2 minus T1. Okay, so what is the slope? In this case, if you have velocity versus time diagram, the slope simply give you delta V over delta T, right? So that's nothing but acceleration. So the slope of a velocity versus time diagram is the acceleration. Okay, so that's the only thing I want to point out. So from there, you can calculate acceleration and everything. Okay. Okay, there's another point I want to make for the general motions here, which is a little subtle, and we don't need to spend a whole lot of time on it. But before we go to a specific problem, let me make another point here. Okay, so let me use another page. There's a point called instant versus average. Instantaneous versus average. Okay. So let's use velocity as an example. Consider velocity. Okay. let's consider two motions. Okay, in one motion. Okay, they in both the two motions, the object goes exactly same distance. So the displacements are the same. Okay, delta x1 equal to delta x2. Let's say also delta t1 equal to delta t2. Okay, so for these two motions, this is 1 and 2. The displacement travel and the time it takes are the same. Now you may conclude say these two motions are the same, identical, but actually they don't have to. You know, for example, you can imagine in the first motion you have a constant velocity. You know, the object, say suppose you're driving the car, right? You move its constant velocity, and then in a certain amount of time you go from one place to the other. Okay. Well, in the second case, it's certainly possible that you drive really fast at the beginning, at the first part of the motion, but then you put over by police, you know, because you go beyond speed limit, right? And then you stop a little bit, and then after that you were scared, you decide to drive under the limit, so you drive like slower. Well, certainly it is definitely possible to finish the same trip, the same displacement in the same time interval, right? But these two are totally different two motions, right? Now, if you so that means for example, if you talk about velocity, right? Because the definition of velocity, like the delta x over delta t, right? So if you have these equal here, the two velocity you got, okay, v1 are going to be equal to v2, okay, because the same ratio you have here. But you know, these two motions are different. That means this velocity you calculate cannot give you a full description of the two motions. It cannot tell the difference between two motions, okay? So the velocity you calculate in this way is actually called average velocity. And this is actually the basic definition. Whenever you see they ask you to calculate average velocity, take the total displacement divided by the total time. Okay, that's how you calculate average velocity. Okay. Sometimes we put a bar on top of the symbol to remind us this is average. This bar in physics and math is used for average. Okay, this means average. Okay, so average velocity. So essentially, we're calculating average velocity. So there's another velocity you can talk about, which is called instantaneous velocity. Okay, meaning velocity at the moment. Okay. Now, certainly, if you can use instantaneous velocity to describe these two motions, you can see the difference, because in the first case, the instantaneous velocity is constant. In the second case, it's changing, right? At the very beginning is really large, and then becomes zero, and then becomes small. So instantaneous velocity give you a better description of the motion than the average velocity. Okay, but on the other hand, if you really think about this concept, right, it's kind of a weird, because we know instantaneous velocity means velocity at this moment, but we know all motion need time. If you don't have time, you cannot have motion. So what do we really mean by velocity at a time moment, right? That seems like a contradictory. So what it really means here is not actually the velocity at the moment, but actually when we calculate instantaneous velocity, we actually use the same kind of formula, delta x over delta t, but we're considering a really short time interval, okay? So the instantaneous velocity is defined as actually something like this. Well, you don't know the meaning of this thing. This is actually taking the limit of delta goes zero. So we were considering a smaller and smaller and smaller time interval, and to get the velocity, and that's a good approximation for our instantaneous velocity. Again, you don't need to know this, okay? So if you want, you can forget about this definition. So what it really says here is instantaneous velocity is a way to measure or calculate velocity is in a very short time interval, okay? Well, you may think that's how do I know it's short or not, right? Well, you actually already use this idea every day when you're driving, okay? When you're driving, you see your velocity on the speedometer, right? What does that number come from? Essentially, it is measuring the velocity in a very short time interval. For example, after every recycle of this revolution of your wheel, right? It can measure the time it takes for the wheel to finish one revolution. And if you know the circumference of the wheel, you can calculate that velocity, right? That is a good approximation for your instantaneous velocity, right? And same thing, like if a police trying to catch you for speeding, right? He couldn't just say that, okay, I caught this guy, he speed up for 0.1 second or something, right? That's too short. I mean, it wouldn't be sufficient. He would probably say that this person has been speeding up for, I mean, over the speeding limit for like in the last couple minutes or something, or at least 10 seconds. Ridiculously, I was caught once for speeding up for less than 1 minute, okay, like 30 seconds. It's like crazy. I feel crazy. So I went to the court, try to argue that, but they didn't buy the argument. But it was right. Like I live in Southridge, so it's right. Like when I go from Southridge to like going towards direction Walmart, you know, that period, that's shorter period. I mean the interval, like the speed limit goes from 45 to 35, but everybody drives like 40 or 45 or something. So I was just like speeding up for that really short distance. But anyway, so you guys, does that make sense to you guys? Like instantaneous velocity. So it gives us a better description, but we cannot really get exactly instantaneous velocity. In reality, we're just taking very short time interval. So now, if you on a space-time diagram, it is easier to understand that concept. So say if you have something like this, you know. So the tangent line of this curve, remember I told you, this the slope of the tangent line is give you the velocity. So as the object moves, you have different slope of the tangent lines. So that tells you actually these correspond to the instantaneous velocity of this object at different moment. Okay, although strictly speaking, we're still talking about a very small time interval. Okay. Okay. Anyway, I think that's enough for this little bit complicated concept. Okay. So far we're done with all the concept. So that's actually the part one of this chapter. It's like introducing the concept for or quantities. Let me say physical quantities. For in kinematics, okay, in kinematics, meaning that we use these quantities to describe motions. Okay, now let's do a. So before we go to part two, let's do a example together. So the example we have is gonna be like, okay, it's gonna be in this section. It's called, where is this? I'm looking for it. It's example, it is example 2.1. Okay, yeah, this one. The tortoise and the hare problem. Okay, so I guess you guys have this textbook, so I'll just read it. Let's take a look at this one. So turtle and rabbit engage in a foot race over a distance of 4 kilometers, and the rabbit runs 0.5 kilometers and then stop for 90 minutes nap, and then upon waking, he remembers the race and run twice as fast. Okay, and so the rabbit finished the whole thing in 1.75 hours. Okay, and it says rabbit wins. I don't know why, but they ask you to calculate A, the average speed of the rabbit, and B, what is the average speed before he stopped for a nap. Okay. Now we're gonna do this one, but we're gonna do it. We'll do a simpler version of this problem, just to make it a little bit easier. So instead of saying it runs twice fast, we'll just say that it runs about the same speed. Okay. Well, twice fast is going to be a little bit harder. So we'll just cross this out. Okay. And we'll run. run same speed. Okay. Okay. Well, it's kind of hard to write on this PDF document. And this is actually also, in some sense, our first problem to solve in this whole class. In chapter 1, we did some simple things like unit conversion, but this is actually like in the first word problem. Okay, in this class, as I mentioned before, we do a lot of word problems. Problem solving is actually a very important part of this class, and only through solving those problems you really understand the subject. Okay? Now sometimes when you sit in lecture, you listen to me, you feel like you understand it, but then when you go to a problem, you have no clue, and that really tells that you don't really understand it. So that's why we need to do it together. Okay. So I mean, we do solve problems. So what we're gonna do is in each chapter, after we introduce some concepts, physical quantities, we'll go to some problems, okay, to apply those ideas we learned to solve those problems, and then we'll try to do some exercise together, and then you guys gonna go solve homework problems. Hopefully, through this whole steps, you can understand the subject. Okay, so how do you solve a problem? Okay, this is our first problem, so I want to do it slow. I kind of like give you a way approach you can use to solve problem in general. Okay. So let me talk about this specific one, and then we'll talk about the some other ones. I mean, some general rule of thumbs. Okay. So how do we solve it? Let me use a different piece of paper. So I would say whenever you try to solve a problem, okay, the good idea is start from drawing a picture. Okay. So let me draw a picture here. Okay. So this is a race of turbulent hair, right? But actually, what in the problem is really just the hair. So let's just, so this is example 2.1, okay? So let me start drawing a, like one-dimensional distance. And then you can define this as your positive direction. Sometimes it's not very useful, but let's just, this is like your coordinate system, you know? And then let's say this is your origin, okay? So then, and if you want, you can draw like make it more interesting. You know, draw a hair. This is the best I can do. Okay, so a hair running. Okay, now then put everything given in the problem. Okay, all the information, quantitative information in the problem onto this diagram. Okay, this help you to look at it from the whole. Okay, let me move this thing to a different. Okay, it's easier this way. Okay, let me put it here. Okay, so see, okay, we see that we know the distance is 4 kilometers, so let's draw the 4 kilometer here. So this is a 4 kilometer. Okay, that's what is given. Okay, and we also see that so the rabbit basically what it does is run 0.5 kilometer and then stops and then run again, right? And then be the okay, so let's put that in there. Okay, so basically we need to separate, we need to divide this into two parts. The first part here is 0.5 kilometer. And then at here it stops, okay? Stops for 75 minutes, right? Wait, is this, oh, 90 minutes, okay. So 90 minutes, okay. And then, okay, what else do we know? Okay, so look at this. And okay, what also says is like he runs same speed. Okay, so basically he runs in both parts same speed, and then he stops in the middle for 90 minutes. And then another thing is he finished the whole thing in 1.75 hour. Okay, so total, you can write total time 1.75 hour. Okay, another thing is like the two speed are same. You don't know the answer. I mean, for the two speed, right? Let's call them V1 and V2 for the first part and second part. Okay. Now the problem in our similar version is as V1 equal to V2, right? So these are all the information given. Okay. Let's see. So let's also try to see what is asked for. Okay, calculate the average speed of the rabbit, and then the average speed before it stopped for a nap. Okay, so part A is average speed. I'll just call it V. Okay, V is like basically the whole motion, right? And then part B is like the average speed before it take naps, so it's going to be V1. Okay, so we're looking for V and V1. Okay, so these are the two things we know. Okay, okay, so now you can go a little bit further to kind of specify exactly what this means. So first of all, this one here, 4 kilometer, right? That certainly means the total displacement, right? You can write like delta x equal to 4 kilometer. Well, this 0.5 kilometer is like your first displacement. You can write delta x1 equal to 0.5 kilometer, okay? And and also you notice this, the time have different units for these two. Well, you need to decide which unit to use. For this one, it seems convenient to use kilometer and hour. So you can convert this 90 minutes to hour. It's basically 1.5 hour, right? Because 60 minutes is 1 hour. So 90 minutes is 1.5 hour. Okay. So you got these kind of information. So now the total time you can write like delta t equal to 1.75 hour. Now, what about this one here? This one is the time is taking rest, right? So if you want to write the total for the actual running time, which is delta t1 plus delta t2. That's, I mean, using this one, that's going to be 1.75 minus 1.5. So that's like 0.25 hour. So the actual running time is going to be 0.25 hour. So delta T1 corresponds to the first part of running, delta T2 corresponds to the second part of running. So that's the given information, right? So you see all these information you have here, they're basically something about displacement, well, and something about time, okay? And then you're looking for something about velocity, right? So that's so again, by writing them like in symbols, it can help you to be able to connect them. So now you're done with your first step. You kind of draw the diagram, a nice diagram. You kind of you can see it, you can visualize it. It helps your intuition, and then you have all these given information written there. So this is everything you know, right? Again, it's sometimes very important to. It seems like trivial, but writing them down and make sure you don't miss anything is a critical step for solving the problem. If you miss anything here, normally it means that you cannot solve the problem. So it's everything given here, okay? Now this is what we're looking for, right? So any word problem can be summarized like this. You have something given, right? And then from this something given, you're looking for the unknown, okay? So this is how, I mean, the question is how you go from the something given to unknown, right? Now there's basically you want to build up the connection. After you build up the connection, you solve the problem. Now, how do we build up the connection? There's actually roughly two different ways you can do it, okay? The first is you start from something given, okay? And then using this to deduce some information here, maybe intermediate information, and then from this you go further until you reach your unknown, okay? This is one way to do it, okay? Another way to do it is you start from the unknown, okay? Now, to figure out if you want to know this unknown, what do you need to know, okay? So you trace backward to something in the middle, and then you trace backward again, and eventually you can trace backward to something given, okay? So that's another way of, basically like you go either from what do you have and then try to figure out, I mean, what you can get, et cetera, et cetera. Or you can go from what do you want to know and go backward and then try to trace back. And well, certainly it's possible for some more complicated problems. You need to do both, okay? You need to go from here to see what you can do from there. And then you also need to go from here to see where is the middle. And then these two paths may meet somewhere in the middle, right? But roughly speaking, that's how you do it, okay? So, but what do we need to connect these two in general? Well, certainly that means we need to know what is the physics behind this the problem, okay? Well, that's certainly the critical step, right? If you know the physics or exactly what formula to use, right, then you should be able to solve the problem. Okay, so how do you figure it out? Basically, certainly it's come from the picture essentially. So as in this one, right, you have this motion thing, and then you're given displacement and you're given the time. Certainly, it suggests that you need to look for the kinematics, like we talked about. And sometimes also because we only talk about so much things, right? So it's kind of if you think about all the things we've been learning, certainly one of them will fit into the problem. Well, in this case, it'd be really simple. It's just the relation between the velocity and the displacement time. So we know in general, the average velocity is given by delta x over delta t, right? So that's like the definition of for our velocity. And that's certainly also just it's pretty much the only thing we learn about velocity, you know, with this formula. So that's certainly something the physics we need, okay, for this problem. Okay. Okay, now let's try to solve the problem part A first, okay? Now, in this, you're asked for a V, right? So if you start from the unknown, right? We want to find out the average velocity for the whole motion. Okay, and so what do we need? Okay, well, the physics is this, right? So it's kind of natural to see that to get the velocity, you want to use this formula, right? From the unknown, right? It traces backward. So basically, using this definition here, we can know that the total displacement, total time, then we can solve for this total average velocity. Do we know these two quantities? What do you guys think? Do we know them? Do we know delta x and delta t? Yeah, send me a message if you yes or no. Yeah, I really like interactions, you know, with you guys in the class. Oh, I got some message. Yes. Okay. Yes. Okay. Yeah, we do. It's pretty clear, right? It's written here. Well, this problem is simple. So you see them directly. So we're given a total displacement 4 kilometer. We're given the total time 1.75 hour. So we just plug in numbers. 4 kilometer divided by 1.75 hour. Okay. And then we'll get our velocity. So at this step, you can take the rest is mathematics, right? So take your calculator, take 4 divided by 1.75. You'll have 2.228. Okay, I'll just 2.29. Okay, kilometer per hour. Notice I capped all the units here so that I can check the units here. Kilometer per hour, it is a unit for velocity, right? So that's the first answer, okay? Very simple. Okay, let's go to part B. Okay, part B is a little harder because you don't really know velocity. Okay, let's say V1, right? So let's try to use the same approach. So to get V1, right, we need delta x1 divided by delta t1. Okay, well, do we know delta x1? The answer is yes, right? Look at here, you have delta x1. Do we know delta t1? The answer is no, right? We don't. Because see, what is given here is only delta t1 plus delta t2, right? So it seems like we cannot get V1 directly by using this formula because we don't know delta t1. Okay, this may make you feel like you're stopped here, right? Because you don't know what to do because it cannot go anywhere from there because you don't know delta t1, right? But let's try the other direction. Okay, try to go from what is given to the unknown. Okay, so we don't know delta t1. Okay, however, we do know delta t1 plus delta t2. Okay, we know that. Okay? And so what does that help? Okay, oh, there's another thing here. Okay. So it seems like we know the total time moving, right? The total moving time, okay, which is this one here. We also know the total displacement, okay, of this motion, right? Now it seems like from there we can calculate the average velocity of this motion, right? Without counting this snapping time, right? And we also know, see, there's a nice relation here, V1 equal to V2 here, right? So that means when the rabbit is moving, it's moving with same velocity or same speed, okay? So it seems like we can calculate, basically what I'm trying to say is we take total displacement divided by the total moving time, which is delta T1 plus delta T2. This would give us the total, the average of velocity of the motion. But because V1 equal to V2, I'll call this V moving, okay, V moving equal to this. But because V1 equal to V2, that's also just the V1. So V1 just equals to V moving. So, okay, so that's good, right? So we can just go ahead and solve this problem, okay? Because we know delta x, which is 4 kilometer. We also know the total moving time, which is delta T1 plus delta T2, which is 0.25 hour. So that gives us the average moving velocity, which is 4 divided by 0.25, which is 1/4. So that's 16. So 16 kilometer per hour. That's the moving velocity of the rabbit. But because V1 equal to V2, so V1 equal to this. So V1 simply equals to 16 kilometer per hour. So that's the answer for the second part. Does that make sense to you guys? Okay. Now, the last step of this thing is to, after you figure out the solutions, you may want to check a little bit, okay? Well, how do we check? There's a different way to do that. You can check like roughly, or you can check exactly. So roughly means like, for example, you got the numbers here, right? And they're in the proper units, right? Kilometer per hour, that's good. And then let's also see whether it makes sense. So in the first case, the average velocity of the whole thing is pretty small. Well, the second case, the velocity here is pretty large. Well, that makes sense, right? Because see, why this is small? Because when you calculate this velocity, you have to take into account the time that this thing, the rabbit stopped for 90 minutes, right? So this certainly slows down the total average because the rabbit spends some time, basically waste some time here. Well, in the second case, we're only talking about the motion, the velocity when the rabbit is moving, right? Certainly it's going to be way higher. Another thing you can see here is you got 16 kilometer per hour. That's not a huge number, right? You don't really know how fast rabbit run, but you can kind of see that 60 kilometer. This unit is a little bit hard to appreciate, but remember, 1 mile equals to 1.6 kilometer. So 16 kilometers roughly 10 mile. Okay, so 16 kilometer per hour is like 10 mile per hour. Okay, so like when you're driving, it's driving really slow, right? So if you feel like it's kind of the rabbit can run like in that speed, right? So it seems like reasonable. Well, if you get, for example, if you get a number like 1,600 kilometer per hour, right? That's like it's like 1,000 mile per hour. You know there's something wrong because you don't think the rabbit can run that fast, right? 1,000 mile per hour. Wow, that's faster than an airplane, you know? So that'd be too big, right? So if you got to enter like that, it'd be like, you probably feel like, oh, there's something wrong. Well, for this number, it seems like reasonable. So this is what I mean by checking like roughly, you know? Well, if you really want to check exactly, you could plug in this back to those equations to see whether they agrees with your numbers to check your mass. But anyway, at least it may be a little bit tedious to do, but at least I would say you need to check roughly to make sure at least these numbers look plausible, you know, look reasonable. Okay. Okay. Any questions? Okay. Another point I want to make here is, again, whenever you try to calculate something like average velocity, you always use this number here. Okay. You always use this equation, v equals delta x over delta t. Just take the total time, total displacement, divide by total time. Okay, that's how you calculate the average of velocity. Okay. Now, if you understand this, let's try to solve another problem, which is let's go back to the initial problem in the book, because in the initial problem it says v2 equals to 2v1, right? So if v2 equal to 2v1, how do we calculate v1, right? So okay, in that case, what you can do here, okay, again, v1 equals to delta x1 over delta t1, but again, you don't know delta t1, right? So you only know delta T1 plus delta T2. So how do we calculate V1 in this case? Okay. Now again, what you can think is this. Okay. So delta X1 divided by delta T1, that's V1, right? Or that's V1. Okay. But we also know that delta X2, okay, maybe let me write here. V2 equal to delta X2 divided by delta T2, right? So this is again, and you know delta X2, right? Because delta X1 is 0.5 and the total is 4. So delta X2 actually has to be 3.5, right? Because that's the rest of the distance you have. So you actually know delta X2, but you don't know delta T2, right? So you don't know delta T1, delta T2. So however, what you can do here is you can try to solve them by setting up this equation, okay? Now V1, as we know, V2 equal to 2V1, right? So this is V2, so that should equal to 2 times V1, right? This is V2V1 equal to V2. Okay. Well, and then from there you can get a relation between delta T1 and delta T2, okay? And okay, let's go ahead and do that. So you have 0.5 kilometer here divided by delta T2 times 2 equals to 3.5 kilometer divided by delta T2, right? So this becomes 1. So you have 1 here, 1 kilometer. So 1 divided by delta T1 equals to 3.5 divided by delta T2. Okay. So from there, you can see that delta T2 equals to 3.5 delta T1, right? But you also know what is given here is the sum of the two equal to 0.25 hour. So from there, you can solve for delta T1, okay? 0.25 hour. Essentially, this is like 2 equations with 2 unknowns, right? So anyway, you plug this back here, you got delta T1 plus 3.5 delta T1 equals to 0.25 hour. That together is 4.5 delta T1 equal to 0.25 hour. So you have from there you can solve for delta T1. Okay, so delta T1 is basically 0.25 divided by 4.5. Okay, so you got 0.0556. Okay, hour. And then now you know delta T1, right? So you can plug it back here to get your V1, okay? So V1, we just delta X1 over delta T1. So you have 0.5 kilometer divided by 0.0556 hour, okay? So this roughly give you about 10 kilometer per hour. Anyway, let me calculate that. Divided by 0.0556. So got 8.99. Okay, 8.99 kilometer per hour. Okay. Well, V2 you can actually solve it as well, although it's not asked, but it's 2 times V1, so it's going to be double of this. Okay. So 17.98 kilometer per hour. Again, the third part is a little bit. The last part here is a little bit complicated. But what I want you to understand is the part A and part B. Okay, these two parts under the simple assumption that V1 equal to V2. Okay, if you know how to do this, you're good. You know, you don't have to do the third one. Okay. So you can actually check the answer here. So yeah, V1 about 9, so it's we got 8.99. They just rounded to 9, so it's the same. Okay, that's so we're good. Okay. Do we have any questions? Okay, so let me kind of. I also want to point out a few things just before we. I would like you guys do a exercise together here to practice on what we just learned. So, but before that, let me talk about one thing. So, let's see. Yeah. So how to solve a problem, okay? Again, the approach we talked about so far, you can summarize like a, I don't know. So basically from given to unknown or from unknown to given, you know. Just that's like the basic method. But to use this method, you need to know what is given and what is unknown, right? But then try to go from, or you can go from both sides, try to, until they meet somewhere in the middle, right? Try to connect them, connection, okay? This is a connect. Connection, maybe I'll call connection, okay? Now, for some more very complicated problems, another way to do, I mean, another simple, like I call like divide and conquer. Conquer. I didn't spell it right, probably. Conquer. So what do we mean by divide and conquer? So if you have something really complicated, what you should do is try to divide this problem into many small pieces, okay? And then try to do this, focus on the small piece once at a time, okay? Now, for example, you want to get A in this class, right? What do? You have to divide by like daily base, right? You do every day, write things, like whenever there's lecture, you listen to the lecture. Whenever there's homework, you do the homework. Whenever question, you ask question. You know, if you do these kind of things day by day, you get A, right? Definitely. And same thing, you want to get a degree, right? In college, how do you do it, right? Again, you have to divide this whole thing into many small pieces, and then just take one course at a time, you know, one semester at a time until finally, and maybe you have a goal for your career, you know, you want to be a doctor or you want to be a astronaut, you know, whatever it is. Again, those big things, you cannot do it by one day or even a month or even a couple months. You have to divide the whole thing into many pieces, you know, divide and conquer them, you know. And let's see. Okay, maybe let me write another one, okay. There's all kinds of things all kinds of simplification, okay. So what do we mean by that? Okay, say you have a problem, right? You do not know how to solve the problem, okay? Now the question is, can you solve a simpler version of the problem, okay? For example, in this example we talk about here, right? The original problem, like this is a little too hard for us. Like this V2 equal to 2V1, it's hard. So you cannot solve this one, but can you solve a simpler version? Meaning that you said V1 equal to V2, can you solve this one? Now you can solve this one, then it may give you some confidence and some experience, and then you can go ahead and solve the original problem, okay? So when you have a hard problem in the task or in the homework, you don't know what to do and you cannot divide it, you know, it's a simple problem, you cannot divide it. And you don't know what to do here, you cannot make connections. What do? You can simplify it and try to solve a simpler version of the problem, okay? Now, after that, then go back to the original problem, okay? In the task, if you just cannot figure out the original problem, just solve the simpler version of it, I'll still give you some partial credit, okay? Just to give you some encouragement, you know? And a lot of times the simpler version of solution give you a lot of suggestions, a lot of hints to a full version problem, okay? So the worst thing you can do here is just sit in front of a problem, stare at the problem, you know, and then say, I have no clue, I don't know what to do, I don't know where to start from, okay? That's the worst thing. You have to start from somewhere, okay? Now, again, as I said, start from drawing a picture, start from, divide the problem or simplify the problem and try to solve the simplified version, whatever you can do, you know, you have to start from where you are and then go to the solution of the problem, okay? That makes sense to you guys? Again, this is only a simple example, but I kind of want to discuss like, maybe the last one here, okay? Write it down, okay? So a lot of times I see students like, as I said, like in the class, they just sit there, look at the problem, I mean, thinking, you know, and I don't know, maybe after a few minutes, you lost what you're thinking. So if you want to think, that's fine, but write whatever you're thinking down, okay? Write things down, help you to think. a lot. Okay, I mean, for a problem as simple as a double-digit multiplication, write it down. Right? I mean, our brain is designed not for good memory. You cannot remember a lot of things in your mind at a single moment. Okay, it's in there, but to use it, you have to kind of think one thing at a time. You cannot put many things at the same time in your brain. Our brain is not really good on that. Computers way better on that than us. But our brain is good at is to figure things out, to analyze things, to create things. Okay, so for that, I really strongly recommend you guys write it down. Okay, write it down. Just don't look at it like a blank piece of paper. It won't help. Okay, write as much as you can. And also for when you're doing calculations, write all the intermediate steps. Okay, write those steps. Okay, because this help you to clarify your mind. Okay, the more steps you write down, the better for you to solve the problem. Okay, now in the test for the word problem, if you only write an answer like a number there, even though it's right, I may take some points off because I don't really know where it come from. For us, the procedure is as important as the final answer. I want to see your thinking process, and you can only show that to me by writing it down. And also by writing down help you to think as well. Okay. I guess I said too much here, but again, this is our first time solving problems, so I want you guys to kind of keep in mind. I think these four kind of rule of thumb is useful for you. Okay. Okay, so with that, let's solve a problem together. Okay, this is going to be our exercise, and again, you're going to get a bonus point by doing this. Okay, so let me move this thing here. Okay. This is not a very hard one, but okay. So think about this problem. Okay, I'm not going to write a whole bunch of sentences here, so I'm going to simplify first. So you are on the street, okay, by yourself. Okay. Now, after the pandemic, right, everybody started coming out. Okay, you see a long time no see friend here. Okay. So at the very beginning, when you see each other, the distance between you guys is 50 meters. Okay. And so when you see each other, right, you want to get together, right? So you guys start run towards each other. Okay. Now you're running with a speed of 5 meters per second. Okay. And your friend is running with a speed of 10 meters. Well, that's too fast, maybe. Let's put 8 meters per second. Okay. So you guys running towards each other really, I mean, pretty fast. Okay, 5 meters per second and 8 meters per second. Okay. The question is how long does it take for you guys to see each other? Okay. How long for you to meet? And the next question is, what is the distance traveled by you and your friend? Okay. Distance traveled by each of you. Okay, yeah, try to solve this problem. Okay. Again, the only thing essentially we need for the formula we need is this formula, v equal to delta x over delta t. Well, you may need a different version of this because this one asks you about the time, right? So you may need this one essentially. Again, try to write everything down. Try to write everything given in the problem, and then write whatever unknown in the problem and try to connect them. This one is not very trivial, but I mean, it's kind of like part B in the previous one, okay? Or part close to part C, maybe, I don't know. But it's not, I mean, it shouldn't be too hard, Yeah, we'll use the rest of this class to do the problem. I'll give you guys about like 10 or 15 minutes to do it, and then we'll talk about this in the last 5 minutes or so. So let me spend the last 10 minutes to kind of explain this. Again, you stop drawing a picture, you know, I already did, but let me draw another one, little, hopefully. So the total distance that need to be traveled is 50 meter, okay? Well, in this case, the two people are going opposite directions, okay? Well, at the beginning, they certainly see like it's like the opposite end of it, but in the end, what's going to happen? Certainly, they're going to meet, right? That means they're going to move to somewhere in the middle. Well, this guy moving is 5, this is why moving 8. So anyway, there'll be probably somewhere here, you know. So right here, okay. Now that means there'll be distance traveled by this person, and then there'll be distance traveled by the second person, right? Delta x1 and delta x2. And now what we're given, so again, try to write what we're given here. So we have V1 equal to 5 meters per second, and V2 equal to 8 meters per second, okay. Now, strictly speaking, because they're in two opposite directions, one of them should be put as negative numbers. But in this case, we don't really care about their direction. We only care about distance. So maybe let me put it like this, okay? So the absolute value of these velocities are 5 and 8, okay? So now okay, so pretty much all we know is these three, right? So we know delta x1 plus delta x2. Okay, again, they're absolute values, meaning distance, the magnitude equal to 50 meter, right? That's the total distance traveled by the two people, right? And then we're given their speed, okay, 5 and 8. Now we're calculating the time it takes for them to meet, right? Well, let's call this time delta t, okay? First of all, there's only one delta t, right? Because say whatever minute happened, right? Because you guys meet together, meet at one point, right? So certainly, basically, it takes same amount of time for this person to travel this much and for the second person to travel a little longer distance. But time it takes is the same for this two motions to happen, right? From here to here, right? So this is the same time. So it's just like it's a single delta t you're looking at, okay? So how do we calculate delta t? Now we know delta t equals to delta x over v, right? Now in our case, we have two of them moving in different directions. So we can write delta t equals to delta x1. I'll take the absolute value because it's just like distance essentially, divided by v1, or delta t equals to delta x2 divided by v2, okay? Right? Now, can we solve delta t from there? We cannot, because we do not know delta x1. We only know v1. We do not know delta x1. Same thing, we do not know delta x2. We don't know v2, but they lead to same delta t. So what we do know is the sum of the two, delta x1 plus delta x2, right? So what we can do is we can set this equal to each other because we know delta x1 divided by v1, okay, equals to delta x2 divided by v2, okay, right? Because it's the same amount of delta t, right? So from there, we can find the ratios of delta x1, delta x2. If you plug in v1 and v2 here, we have delta x1 divided by 5 equals to delta x2 divided by 8, okay? So from there, we can write, we can say, for example, delta x2 equals to 8/5 of delta x1, okay? Now we also know the sum of these is 50, right? So you plug this into this. Again, there's like two unknowns of these two equations. You get delta x1 plus 8/5 delta x1 equals to 50 meter, right? So from there, you can solve for delta x1. So it's 1 plus 8/5, so that's 13/5 equals to 50. So delta x1 equals to 50 times 5 divided by 13. So if you take a calculator, you got 250 divided by 13. Okay, that's okay. That's like 19.2, okay, for delta x1 meter. Yes, so now you see back here, right? Now you know delta x1, you know v1, you can calculate delta t, right? So delta t equals to delta x1 divided by v1, so it's 19.2 meter divided by 5 meter per second, okay? So that's like 19.2 divided by 5, which is 3.84, okay, second, okay? Well, the distance travel, we already got delta x1. So another distance will be just the delta x2 equals to delta x divided by minus delta x1. So 50 minus 19.2, that's basically 30.8 meter. So yeah, in some sense, this one's a little complicated because this is kind of like the third part we did here. Okay, you have to solve two unknowns with two equations. Okay, now some of you may did a little bit differently. If you think about this as, okay, I got, okay. Yeah, some people got like a 3.75. That's maybe the rounding issue, because I got 3.8 something, you know. Anyway, so another thing you can think about is like, see, these two people are going towards each other, right? So because they're going towards each other, in some sense, you can think about from, for example, from this person's point of view, right? If you think this person is staying at rest, then this person is going relative to that person with 13 meters per second, okay? Now you can take 50 divided by 13, you get exactly the time, 3.84. Some of you may did that way, because then this, I mean, this is a little bit faster way. But if you don't understand what I'm talking about, then it's probably better to look at this first way, okay? Again, this is a little bit complicated, but hopefully you understand based on what I said here, okay? How it works. Any questions? Now you can check that delta t should also equal to delta x2 divided by delta t2. Delta x2 divided by v2. So 13.8 divided by 8. Divided by, is that 8 or 8? Yes, 8. Divided by 8. So this should give you the same thing, you know, 30 point. This is like a way to check as well, see whether it's self-consistent. Yeah, you got 8.85. So, sorry, 3.85. Well, there's a 0.01 second difference, but this is mostly due to rounding issues. So it's a little bit uncertainty in the last digit, but other than that, it's the same. Okay. So we're done with our first part of this chapter. We're done with the introduction of all the kinematic quantities and how they work. And by doing this kind of problem, we can see how to use them to calculate mostly the average velocity. Now, in the second part, which we're going to start tomorrow, we're going to go to, we'll apply to what we learned to some simple motions, mostly constant velocity motion and constant acceleration motion. And then we'll solve some problem about these specific motions, okay? So right now, you can start doing your homework in chapter 2, but when it says constant acceleration motion or something, just ignore it because we haven't talked about that yet, okay?